Hey guys, back for some more AP Chem. We're going to move into chapter 7 here. Not going to go too far, but a little bit. Here we go, but we need jokes. That's all we really care about. Did you hear about the fight in the fish shop last night? The fish shop. 2 fish got battered. That wasn't very good, was it? Let's see if I got any more that are good. What do you get if you try and cross a mouse with a skunk? Dirty looks from the mouse. I don't think that's any good either. Okay, so here we go, into chapter 7. And again, we're going to try and get through this by the time we get to the end of the semester, by the time we get to Christmas vacation. So here we go. The problems in chapter 7. Chapter 7 is, I was just telling Megan's in here working on test corrections. It's kind of unfortunate because one of the things that they don't test on the AP test is there are these things called quantum numbers, which I always like to spend a little bit of time on. I think they're kind of fascinating to see how they work. But because of obviously the time limitations, we are not going to do those. So what we're going to do in chapter 7 is kind of like 2 small chapters put together. It's on atomic structure, kind of going back to electron configurations. And we're going to start off here talking today about waves. And the reason we're going to talk about waves is because waves are what are used to understand some things about electrons and their transitions in energy levels. And then we're going to connect the atomic structure and electron configuration, electron arrangement to the periodic table. And then we'll be able to predict some properties on the periodic table. Okay, so here are the problems. So again, it's 2 small chapters put together. In this chapter, I always typically do 2 labs on this thing called, with this instrument called a spectrophotometer. But again, because of time, we will definitely do 1. And I doubt we'll probably do it in January. But like I said, we start off this chapter. So again, it's about atomic structure and periodicity. So we're going to, again, really connect atomic structure, mainly about the electrons and the electrons arrangement outside the atom to the periodic table, to be able to predict the periodic table. But we're going to start off talking about a topic that is more of a physics topic, which are waves. But the reason we're going to do that is to understand electrons and their transition from energy levels. The light they give off, the energy they give off in the form of light is in the form of waves. So we're going to spend a little bit of time on waves, which will help us describe, again, eventually the electrons. So 4 characteristics of waves. The wavelength, like this picture is showing the wavelength. If you just think of the word wavelength, it's the length of a wave, the length of the top of one wave to another, the distance between successive peaks in a wave. The symbol for that is the Greek letter lambda. And actually, if you look on the formula sheet, the very front, they even have it right over here. It's the 3rd one down. So you have energy, frequency, and wavelength. That symbol's the Greek letter lambda. And then frequency, and that little thing, it looks like our letter V, a lowercase v. It's actually the Greek letter nu, N-U. And frequency is like frequent. So it's how many waves come pass a point per unit time. And if you look at the picture there on the lower right, you can see the red waves, the green waves, and the blue waves. And you can even see there's, for the red waves, it's 4 cycles per second, or 4 hertz. The green ones are 8, and the blue ones are 16. So how many waves come by a point per certain time? Notice the unit there is it's a hertz. And a hertz means the same thing as waves per second. So kind of like the rental car company hertz. And then amplitude is the height of the wave. And this is like when a really good song, you guys probably don't even listen to radios like I do, but if you listen to the radio and you're listening to a good song and you really like the song, you turn up the volume. Well, you're turning up the amplitude, the height of the wave when you do that. Okay, and then the speed. the sound travels about 1,000 feet per second, where light travels 186,000 miles per second. I'm just going to figure this out myself. So if you think about how fast light is traveling, in 1 second, light travels around the Earth about 7.5 times. So in that second, light goes around the Earth almost 7.5 seconds. This is why, like, I'm a golfer, and so whenever a storm comes over, you've always got to watch. And of course, do you see the lightning bolt or do you hear the thunderclap at first? And the answer is you always see the bolt, because light travels faster. And if you count, so when you see the bolt and you count 1,001, 1,002, if you get up to 5, then that thundercloud is a mile away. So for every count of 5 is what I've learned. Which travels faster, sound or light? Light. A 5-second count after a lightning bolt tells you how far away. A count of 5 means it's 1 mile away. So light travels about 1,000,000 times faster than sound. Okay, and this again, I'm just going to go through, this is again more of a physics concept, but light, which we're going to talk about some in this chapter, is a form of electromagnetic radiation and energy that travels through space in the form of light, or in the form of waves having fluctuating electric and magnetic fields. So again, we're going to talk about waves, but we're going to kind of just leave it there. This is the electromagnetic spectrum. And you can see that symbol up there above X-rays is a gamma ray, and then X-rays, ultraviolet. The part that we can see, you see the visible part of the spectrum is actually a very small part of the spectrum. And then infrared, microwave, and radio waves. And if you look on this, you can see the top are frequency, the bottom are wavelength. Okay, and this is just, if you know anybody that has had cancer and the treatment, sometimes they are given radiation treatments. That actually, my wife was like this many years ago. She had breast cancer, and she had like 30 days of radiation treatments, and that's what this is. So X-rays and gamma rays are both called ionization because their short wavelengths correspond to high energies. When ionizing radiation interacts with biological molecules, it can permanently change or destroy them. And so that's why doctors use that. And of course, the unfortunate part about that is that when doctors use this, they not only kill the cancer cells, they also kill the good cells. And that's why sometimes people get sick with it. Okay, and all forms of light travel at the same speed. And what is the relationship between wavelength and frequency? They are inversely related. So as you look at this, as the wavelength goes up, then the frequency goes down. So they are oppositely related. So a smaller wavelength means a higher frequency, and the opposite is the case as well. And here is equation number 1 in this chapter, which again is on our formula sheet. It's right on the front. It's actually the second one down. So C, the speed of light, which is, I always just use 3.0 times 10 to the 8th meters per second. You can see they give it as 2.998, the AP does, as 10 to the 8th. I said negative 8th. I should have said 3.0 times 10 to the 8th meters over seconds. Okay, so here's equation 1. And this, like I said, I wasn't going to make this be a very long lesson. So I'm going to do one set of problems here, and then we'll be done for today. Okay, so I want to actually do these 2 problems. Okay, so I want to, for C, the speed of light, which is given to you, 3.0 times 10 to the 8th meters per second is equal to the wavelength times the frequency. So I want to calculate the wavelength of 2 radio waves. The FM radio wave, MHZ, stands for megahertz. And then the AM radio signal, which is KHZ, which is kilohertz. And I want to determine the wavelengths of both of those. Okay, so this is what we're going to do. Okay, so again, writing here on the board. So on our formula sheet again is that equation I was talking about. It's right there. It's the second one down. And you can see over here too that the speed of light, I'm just going to use 3.00 times 10 to the 8th meters over second. So this is what I've got. So I've got the speed of light, which is equal to 3.00 times 10 to the 8 meters over seconds. And just to be simple, instead of using the Greek letters, I'm just going to use F for frequency and wavelength. Again, make sure you know that frequency goes up, wavelength goes down. Later in the chapter, we're going to throw energy in here, and we'll say that energy is directly related to frequency. So as the energy goes up, the frequency goes up as well. Okay, what we're given in these two problems, we are told that the wavelength is 105.9 megahertz. Remember the units. Frequency is in Hz or hertz, and wavelength is a unit of length. It'll be in meters. So I want to get the megahertz into hertz. So I'm going to take for every 1 megahertz, and here the key thing is the prefix, mega. There's a million hertz. Rarely do we ever use a mega, but we are on this problem. So that gives me 105.9 times a million. That gives me 1, 2, 3, 4, 5. So I've got so this is how many hertz I have. Okay, now to figure out, so now I'm going to go back to this. So now I know the wavelength. I'm trying to solve for the frequency. So I'm just going to use this equation. So I got 3.00 times 10 to the 8 meters per second. Again, units are going to kind of be my guide here. Frequency is what I'm trying to find. And I'm going to plug this in for the wavelength. So I got 105,900,000. Sorry, I'm messing up. That's the frequency. That's the frequency. I plugged the wrong things in. So that's 105,900,000 hertz. Remember a hertz means 1 over seconds. That's what a hertz means, 1 over seconds. So I'm going to use that here. And then I'm trying to solve for the wavelength. The wavelength is x. Okay, so if I solve then for the wavelength, so again, just like you guys know, I want to isolate on one side of the equation my unknown. So if I do that, now seconds cancel out. And so what I have here then, the wavelength is going to be 3.00 times 10 to the 8th divided by 105,900,000 gives me 2.83 meters. Unit is meters. Okay, so that is the wavelength. This is of the FM radio signal. Okay, now over here, I'm going to do the AM radio signal. So I'm going to use the same equation. So I'm going to use 3.00 times 10 to the 8 meters per second. That's C. Okay, and it's equal to frequency times the wavelength. Okay. Well, we are told that this is the frequency we're told is 850 kHz. That's a kilohertz. So I'm going to get this into hertz again, just like I did in the other problems. So for every 1 kilohertz, there's 1,000 hertz. So it's going to give me 850,000 hertz, which again is 1 over seconds. Hertz means 1 over seconds. Okay, so now I'm going to come back here. So I've got 3.00 times 10 to the 8th meters per second. And it's equal to the frequency, which is 850,000 seconds, or 1 over seconds, units, right? Times wavelength, which is what I'm trying to solve for here. Okay, so if I solve for that, you're done, Megan?
Yeah.
So seconds cancel out. So then if I do this on my calculator, to get is X is equal to 353 meters. Okay? And again, like I was talking about in class just even today and yesterday, when you do a problem in our class, it's always kind of good to kind of ask yourself, see you, Megan, have a good weekend. Does that make sense? Well, here, this is the AM signal was 353 meters. The FM signal over here was 2.83 meters, but we're going to talk about later that wavelength and energy are opposite. So a shorter wavelength is more energetic. And so in a way that does make sense. An FM signal is more energetic than an AM signal. Okay, I'm going to stop there. We're going to kind of get into chapter 7. Right now you need to be getting ready for chapter 6. So hey, have a good day, and I will talk to you guys soon.